Today is the day 6 of 75 hard research challenge, and I'm going to take a review now of what I studied yesterday, that is on the day 5 of this 75 hard research challenge. So last time we saw what are absolute position embedding in transformers. So today we are going to look at what are relative position embeddings in transformers. Okay, so the focus of absolute position embedding is that, let's say you are given a sequence like this, right? So it wants to focus on a position I, and it only focuses on that position I to get the position embedding. For example, you have position embeddings P1, P2, P3 and so on till up the maximum length PL. Okay, in the case of relative position embedding, the focus is on representing a pair of tokens. That means you would like to represent the I and jth pair for all I is equal to 1 to L and j is equal to 1 to L. So that implies that you will have a positional embeddings for P12, P11, P13 and so on and so forth, P21 and so on and so forth, right? So what are the properties? Generally can be added directly to the token embedding. For example, we saw that just give me a second. Yeah, so we saw that we wanted to have a attention matrix here, where we take a softmax over k qk transpose divided by root dk. And here in this case, in a general case, what people do is, or in the absolute position embeddings, for example the original paper, what people do is that they say that we multiply wq with the content as well as the position of the content. Okay, so this is not usually the case for relative position embeddings. Okay, we calculate the attention matrix separately and then edit it or modify it using the relative positional embedding. This is the general case. There may be some variations of it. The very first popular paper on this was ALiBi. Right, in this paper what they did is that they simply said that you have originally earlier absolute embeddings are like this: the wk ci is the content embedding and pi is the position of that, and similarly you compute the kj, which is the jth query. Okay, so we compute the qk transpose like this: q1 k1, q2 k1 and q2 k2 and so forth, and this is the mask that we have. And in this case we see that the qk transpose itself has the positional embeddings because you have added these here, right? So in case of ALiBi, what they say is that do not do this. Simply what you do is that you compute qi and ki like this, and then you compute your attention matrix, attention scores q k transpose as earlier you were doing. This is the mask, right? But then once you have computed this, you add position another matrix of the same size, right, with certain properties. This is going to represent the positional embeddings. So in this case, all these values are 0. That means position embedding of I comma I is equal to 0. That means there is no positional bias that you, or positional encoding that you want to add on a particular word token at the ith position, right, for itself. And as you move away, let's say you have a position, you have a sequence with you, and this is the ith word that you want to see. Let's say the ith I is equal to 2, so that would mean I is equal to 0, I is equal to 1, I is equal to 3, right? So this particular row that we are looking at. Okay, so what does that mean? That as you move away from I, if this is the query and these are the keys, right? Right, so for itself you use a positional embedding of 0. That means when you attend on yourself, you use a 0 positional vector, right, positional bias in this case. But in case of others, what you do is that you continue to decay it in a way as you move away from that. For example, if the positional encoding of this I is equal to 2 for I is equal to 0 in this case would be -2, and for I is equal to 4 would be +2. So essentially what you are doing is that as you move away from this particular node, you use a position encoding of -1, -2, -3, and on this positive direction you use a position embedding of 1, 2, 3 and so on. But how long will you go? That is also a question. So in this case, in this paper, they say that you have some minimum and maximum ranges of on both the side of the query position that you are querying. In this case, it would be I is equal to 2. Beyond that, you simply say that all the positions have the same encoding. For example, in this case, let's say 4 is the value, then you get -4, and then 5th position will again get -4, 6th position will again get -4, and in this side you get 4, 4, 4 until whatever sequence length you have. The intuition behind that is that as you move away from your query node or query token, beyond a certain distance from the query node, it does not matter how far away it is. Usually your attention should decay and should stay constant beyond a particular range. Okay. In this case, what happens is that words that are closer together have higher dot product. Further, you multiply this particular matrix with a value m, which is a hyperparameter. They call it as a slope, and it varies from one attention head to another. For example, the first head can have a value of 1 by 2, 1 by 4, 1 by 8, and not. Okay. In the paper of ALiBi, what they have done is they have kept this attention matrix as fixed, but they have also tried learning it, but it does not help. Okay. There are certain questions that we would like to answer here. First one is that ALiBi helps in extrapolation. How does it do that? Second, we note that positional encoding only affects the q and k and not the value vector. So what you are essentially doing is that you are treating a value of a particular token, the value vector of a particular token, independent of the position it is located at. As the distance between positions increases, ALiBi will decay to a point of vanishing, which is a problem, right? Because then you may have long range dependencies between yourself. Now we are going to look at some of the graphs that ALiBi showed. On the x-axis, you have inference input tokens. That means the length of the sequence at the inference time, at the test time. There is no training going on. It was trained for 512 tokens. Okay, and this graph shows when you train it for 1024 tokens. Again, the x-axis shows the inference input tokens. The y-axis shows the perplexity. We saw in the couple of videos earlier from this one that perplexity, the lower the value, the better it is. Perplexity essentially is telling you the negative log likelihood of what is the, it is like directly proportional to that negative exponential of log likelihood of the word that is going to be generated next, or the sequence to be generated next, right? So as you can see that this is the sinusoidal graph. So this is the sinusoidal one. So as you can see, as we increase the number of tokens during test time a little bit more than what we saw during the test during the training, that means 512 in this case, then the perplexity drastically increases, almost like exponentially, right? Whereas in the case of other embeddings like T5, and we will see what is T5 in a couple of minutes, and what is rotary, which we will see in the next lecture, that means tomorrow, and ALiBi, we compare these, right? So as you can see, all of these relative position embeddings, these two are also relative position embeddings. This is absolute position embedding, right? So this is absolute position embedding, this is relative, this is also relative, and this is also relative. So as you can see, as the value of the number of tokens increase during inference time, the perplexity for ALiBi does not grow and it goes flat. And this is the same case as it happens in the 1024, when 1024 tokens are taken during the training, and we, let's say, extrapolate it to 16k tokens. Okay. We'll move on to the next part, which is rotary positional embeddings. We'll start with the paper, but the paper discusses a lot of relative positional embeddings, so we will cover that part in this lecture and leave the exact details of the rotary positional embeddings to the next lecture. Okay. Okay. So we know, let's formulate the sinusoidal positional embedding, which is the absolute positional embedding, in a different format. So what do we want? We want that we have QM, that means a query at mth position token k at nth position and value at nth position are given by a function fq, fk and fv respectively. Fq is a function of token at mth position and the mth position itself, right? Similarly, the key kn, the key vector at kn nth position is a function fk which takes two arguments xn and n. Similarly for vn. Okay, we note that in this case for sinusoidal positional embeddings, the query key and value vectors are a function of the position, absolute position, right? So we saw this particular equation earlier. Okay, they come essentially. What happens is that you compute this attention score like this. You take the dot product between qm and kn. Let me zoom in a little bit. You take the dot product between qm and kn, normalize it using the dimensionality of the vectors. You take an exponential of it. Essentially, you are taking a softmax here. Okay, and then you simply divide it, normalize it with the attention of other key values for the same query. Okay, so essentially what is happening, I'm just revisiting it again, is that if this is your mth query, then mth query will have to attend on all the key values including itself, right? So that is what is happening here in this. We have a j vector, j value, right? Okay, so and then you simply in the end you the value or the output at mth token is simply a weighted sum of the values at over all the n here, right? Okay, now let's look at what is relative positional embedding. There was a paper by Shaw et al. I think it was in 2020, 19 or 20, I do not recall. But they say that you do not add any positional embeddings in the query. Okay. So FQ in their case, as we saw here, FQ they are now going to define FQ, FK and FV. So FQ in this case is simply WQXM and has like no positional embedding here. But FK and FV will have a positional embedding. But note that earlier what did we have? We would have had with us in the sinusoidal case Fk x n comma n would have been Wk xn plus Pn, correct? But in this case, note that they do not do this. What they say is that replace Pn with the relative embedding. This was earlier a positional embedding. So they will say that replace it with Pr. And R is equal to, in this case, minimum of, R in this case is simply this particular value. That means you take the distance between the query position and the key position, right? This particular m and this particular n, and you cap it to R min and R max as we saw in ALiBi, right? Okay. So this position PR is now a relative position rather than an absolute position as it was earlier in the case of sinusoidal embeddings. Okay. Now what does that mean? That also means, just to ground it a little bit, that if you have a query at position 2 and a key at position, like, okay, this is query, this is key, that means n, then R is equal to 2, correct? Also, if you have a query at, let's say, m is equal to 6 and n is equal to 8, then also you have 2. So that means both of these are going to share the positional embedding P2, right? Okay. This is what I have explained in this particular image also. Okay. So as if m is the query, then you use P0, you move in this direction, you use I think it should be right, you use P of -1, P of -2, and let's say you cap it to here, then you use P of R min, then P of R min as you go away from P0 after a particular threshold. Similarly on the positive side. If you move away from P naught after a certain distance, everything is PR max. Okay. Similarly, there are other papers that did the same thing with relative positional embedding. For example, there was a famous paper, Transformer XL. In this paper, what they did is they expanded the sinusoidal formula. For example, in the sinusoidal formula, we saw a couple of lectures back. Let me zoom out a little bit. Yeah. So what we did is that in this case, what we had is that we expanded this particular right formula to get these four terms which were attending on between other right query and position and query and key and so on, right. So we'll let me just revisit it here again. In the case of transformer XL, what happens is that let's say you want to expand this particular value for the sinusoidal positional embedding. So this is the formula that you will get. How did you get this to this formula? Okay, so what did we have? We have WQ. Let me write it somewhere here. Okay, so you had Q transpose MKN is equal to WQ and into XM plus PM, correct? And you take a transpose of this, okay, and then you also have WK XN plus Pn. Okay, so when you expand it, it is simple a decomposition rule. You get this particular equation. Okay, so once you have this particular equation, let's see what goes on. So a lot of papers around relative embedding said that you replace the position embeddings here Pn and Pm with certain relative values rather than absolute values. That's all everybody is doing. There are 5-6 papers around it, or maybe more than that. Okay, so we are going to look at what Transformer XL did. So it did 2-3 things. First, it did is it replaced, it said that make Pn relative. That means some positional embedding m minus n, as we saw earlier in this case, right, in the relative position by Shaw et al. Okay, so then it said for the case of PM, when you, where is PM? Let's see. So where here is PM and here is PM. So now in this particular formula, what is happening is that you are taking the attention of position as query with xn as key, and in this case you are taking the position as query and position as key also, another position as key. So they say that use different values for these and this in this case, that's all. So they say they use u here and v here. Okay, third thing they did is they use different wk for content and position. Okay, so they say that now that you have divided the sequence into two parts, inputs at the sequence at two parts, that means you have a position and you have a content which is represented by x here. You use different values for wk here, you do not share the weights there. So that essentially means that you end up with this particular equation, that you leave this particular thing as it is. Okay, then you replace Pn with the relative embedding everywhere. These are two positions. Okay, third, what you did, you replace PM in this position and this position with U and V vectors respectively, where U and V are randomly initialized and learned as we train using backpropagation, as we train other parameters of the model. Okay, third thing you did is that because earlier this WK and this WK were shared, but they noted that this WK is being applied in the case where you take attention between two contents xm and xn, whereas this wk is again being used with xm and a position. So it would be better to not share the weights of this, because the input for this is different than this. Okay, so that's all they did. They have different weights here, that's it. Okay, right. Okay, so similarly, there was another paper, a famous paper called T5. In this case, what they simply did is that when you had this particular equation with you, they said keep this as it is, replace everything, all these three terms with a single learnable bias term, that is a relative. Okay, so last three terms are replaced with a bias term, which is again learned and is relative. Okay, and another relative position encoding, what they did is that they said that you keep this also, but replace the middle two terms with the attention between pm and the positions of the query m and the key n, and use different weights than you used to get the computation for content xm and xn. Okay, so this is all for today. I'm going to talk about rotary positional embeddings tomorrow. So stay tuned and thanks.